In this video, I'm going to demonstrate how to perform k-nearest neighbors in R. As mentioned earlier, in order to evaluate the accuracy of the KNN algorithm, as well as determine the appropriate value of k, we generally perform cross-validation using either the holdout method or the k-fold cross-validation method. Most data mining packages in R allow for the k-fold cross-validation method, which when compared with the holdout method is less sensitive to how the data are partitioned. Furthermore, when we use the k-fold cross-validation method in R, we only need to divide the data set into two partitions, training and validation. We apply the k-fold cross-validation to the training data to find the accuracy rate associated with each choice of k. And then we apply the best k to the validation data set to get an assessment of the model's predictive performance on unseen data. Depending on the amount of data available, when cross-validation is performed, most practitioners partition data into either 60% training and 40% validation, or 70% training and 30% validation. In this example, we are going to divide the data in the gym data worksheet into two partitions, 60% for training and 40% for validation, and then implement a tenfold cross-validation technique. Now in RStudio, I have imported the data from the gym data worksheet of the gym data file into a data frame and labeled it My Data. The dataset comes with 4 variables, in row, which is the target variable, and 3 predictor variables, age, income, and hours. For KNN estimation and the resulting performance measures and diagrams, we need to use a number of R packages, including correct, gains, and ROC packages. Please go ahead and install these packages if you haven't done so already. If you have already installed these packages, as I have, you can launch these packages using the library function. Now let's start a new script. Now let's run these 3 lines of code to launch the packages. Let's first take a look at our data using the head function. As you can see, we have 1 target variable in row and 3 predictor variables, age, income, and hours. As we discussed in the lecture, KNN uses the Euclidean distance to find the nearest neighbors in the training data. Euclidean distance is highly sensitive to the measurement scales used in the dataset. For example, in this dataset, income, which is measured using much larger numbers, will have an oversized influence on the distance measure than age and hours, which are measured using much smaller numbers. In order to remove the impact of the measurement scales, we should standardize the data into z-scores, which are unitless measures. We can use the scale function to standardize the predictor variables in the MyData data frame in this case, and store the z-scores of the predictor variables in a new data frame called MyData1. Since we only need to standardize the predictor variables, we will apply the transformation only to column 2 to 4 in this dataset. Now let's take a look at my data1 data frame. As you can see, the predictor values have been converted into z-scores. But my data1 data frame only contains the z-scores for the predictor variables, so we still need to add the target variable in row back into the dataset. So this is what I'm going to do now. Here I have combined the standardized predictor variables and the target variable in row into the same data frame, and changed the column name of the target variable in the new data frame to in row. Let's run these two lines of code. And then let's use the head function to take a look at the new data frame. As you can see, now my data1 data frame contains both the 3 predictor variables and the target variable in row. Since our target variable in row should be a categorical variable, even though it's in numeric form right now, it indicates whether the potential member enrolled in an annual gym membership or not. So to properly set this up, we're going to use the as.factor function to convert the target variable in row into a categorical data type called factor. Now let's use the structure function to double check to see if the target variable in row has been converted into a factor variable. As you can see, the target variable in row has been converted into a factor variable with 2 different levels, 0 and 1. To partition the data into 60% training and 40% validation, we use the create data partition function and specify enroll as the target variable. To ensure that we all get the same data partitions, we are going to use the set.seed function to set the random seed to 1. Let's run these 4 lines of code to partition the data. As you can see, we are partitioning the data into 2 data frames, one called train set and the other is called validation set. Now we are going to set up the k-fold cross-validation for KNN analysis. First, we need to specify the number of folds and the method of cross-validation using the train control function. And we stored the specifications in an object called myControl. The method option specifies the method to be cross-validation, and the number option specifies that we are using 10 folds, which randomly divides the training dataset into 10 partitions. Now let's run this line of code. Now we are going to use the expand.grid function to specify possible k values from 1 to 10 and store the results in an object called myGrid. The possible range of k values may vary. You may experiment with a different range by changing the numbers in the statement. To implement the KNN method with the training dataset with option values specified in the previous steps, we are going to use the train function and store the results in an object called KNN_fit. Again, to ensure consistency of the cross-validation results that we get, we are going to use the set.seed function to fix a random seed. In the train function, we specify the model, which uses enroll as the target variable, and the tilde and the dot means that we will use all other variables in the dataset as predictor variables. We will use the standardized training dataset and the KNN analytical method. Let's take a look at the cross-validation results from KNN. Now let's run these 3 lines of code. And let's take a look at the cross-validation results from KNN by typing in the name KNN_fit. And let's run it. Now the result shows the accuracy across choices of k from 1 to 10. The accuracy values are the average accuracy from the 10-fold cross-validation. As you can see, k equal to 6 provides the best accuracy rate of 0.91. The model will use k equal to 6 as the final value for k. We now are going to apply the KNN model, which uses k equal to 6, on the standardized validation dataset using the predict function. And then we use the confusion matrix function to create a confusion matrix. We are going to store the prediction result in an object called KNN_class. The predict function specifies that we will apply the KNN_fit model that we just created to the standardized validation dataset. The function will produce predicted class membership of the cases in the validation dataset using the default cutoff rate of 0.5. The confusion matrix function requires 2 parameters. The first one is the predicted class membership, and the second one is the actual class membership in the validation dataset. The optional parameter, positive, specifies which class is the target class or the positive class. Since we are more interested in those who actually purchased an annual gym membership, we will use 1 as the positive class. Now let's run these 2 lines of code. Okay, so as the confusion matrix shows, the model has an overall accuracy of 0.91, sensitivity of 0.89, and a specificity of 0.93. This suggests that overall 91% of the validation cases are correctly classified, and among the target class cases, 89% are correctly classified, and among the non-target class cases, 93 are correctly classified. Overall, the model has a pretty good predictive performance. To evaluate the predictive performance of the KNN model, we can also compare its predictive performance measures to those of the naive rule, where all cases are classified into the predominant class. Because there are 161 target class cases among the 399 validation data cases, the naive rule would classify all cases into the non-target class, which is do not enroll in the gym membership, and would produce an accuracy rate of 399 minus 161 divided by 399, which is 0.5965, and a sensitivity of 0 and specificity of 1. Therefore, the KNN model shows better predictive performance than the naive rule does, especially if the goal is to identify target class cases. We have also discussed that sometimes the default cutoff rate of 0.5 is not necessarily the best cutoff rate for the situation. The analyst may choose to increase or decrease the cutoff value to classify fewer or more observations into the target class due to asymmetric misclassification costs and uneven class distributions. In this example, the opportunity cost of missing a potential gym member who would have purchased the gym membership is likely to be higher than the cost of reaching out to a potential gym member who ends up not purchasing a gym membership. Furthermore, among the 1,000 past open house attendees in the dataset, 403 purchased the gym membership, suggesting that the probability of an open house attendee purchasing the gym membership is about 0.403 instead of the default probability of 0.5 for a binary choice situation with equal class distribution. In this case, the manager of the fitness center may want to reduce the cutoff value to a lower value than 0.5 in order to classify more cases into the target class in order to achieve a higher sensitivity value. Let's see what happens if we lower the cutoff rate to 0.25. To do this, we first need to compute the predicted probability of each case belonging to the target class by setting the option of type to prob in the predict function. And let's take a look at the first few probability values. Let's run these two lines of code. This shows the probabilities associated with the first few cases. As you can see, the first column lists the probabilities of the cases belonging to class 0, which is not enrolled in the gym membership, while the second column lists the probabilities of the cases belonging to class 1, which is enrolling in the gym membership. To determine the class memberships of cases using a cutoff value other than the default probability of 0.5. We are going to compare the values in the second column to the new cutoff value. To construct a confusion matrix using the new cutoff value of 0.25, we use the if-else function to determine the class memberships. We use the as.factor function to convert the class membership to factor, which is the same data type as the target variable in row. Now let's enter the command. Now let's run this line of code, and we get a new confusion matrix. As you can see from the result, when we lower the cutoff value to 0.25, the model's overall accuracy and the specificity decreased to 0.88 and 0.82 respectively. But the sensitivity increased to 0.96. If the goal is to identify more potential members who would end up purchasing an annual membership, this cutoff value would allow us to catch 96% of these members. Now let's create the graphic performance measures, including the cumulative lift chart, decile-wise lift chart, and ROC curve. These performance measures are important because they are not affected by the choice of cutoff value as the confusion matrix does. Both the cumulative lift chart and decile-wise lift chart are constructed from the gains table that can be created using the gains function in R. The gains function requires that we convert the target variable into numeric ones and zeros. It is important that we first convert in row into characters, then to numeric variables. If we directly convert a factor variable into numeric variables, instead of having zeros and ones, it will become ones and twos. Now let's run it. We then create the gains table using the gains function. Let's run this line of code. As you can see, the gains function requires two parameters. The first one is the target variable in row of the validation dataset, and the second parameter is the predicted probability of the validation cases belonging to the target class. Now let's take a look at the gains table by typing in the name gains underscore table. By default, the cumulative gains table divides the cases into 10 groups based on their probabilities of belonging to the target class. The last column of the gains table shows the average probability for each group. Please note that these values are rounded to 2 digits after the decimal point. In R, in situations where there are less than 10 possible probability values, the cumulative gains table will show less than 10 groups, and you will get a warning message. So if you do get a warning message, you can ignore this warning message in this particular case. But in our case, we do have 10 groups, so we didn't get a warning message. Now let's take a minute to understand the gains table. The first column is the depth of file in percentage. The second column is the number of cases in each group. The third column has the cumulative count of the cases. The fourth column has the mean response for each group. In other words, what percentage of the cases actually belong to the target class. For example, in the first group, with 59 cases, 93% of them actually belong to the target class. The fifth column has the cumulative mean response. For example, Group 1 and Group 2 together, 92% of all the cases actually belong to the target class. The sixth column is the cumulative percent of total responses. For example, the first group contains 34.2% of the total cases that actually belong to the target class. If we combine groups 1 and 2, they contain 68.9% of the total cases that actually belong to the target class. The seventh column contains the lift index for each group in percentage. For example, it shows that in the first group, which includes the 15% of the validation cases that have the highest predicted probability of belonging to the target class, the KNN model is able to identify 231% or 2.31 times as many actual target class cases than if a random 15% of the validation cases are selected. This is an important indication of the model's performance. A lift index higher than 100% shows improvement in prediction compared to random selection. The eighth column shows the cumulative lift. For example, if you combine groups 1 and 2, which contains 30% of the validation cases, you can achieve a cumulative lift of 227% or 2.27. And finally, the last column contains the predicted probabilities. To construct a lift chart, we use the following command. This command plots a line chart with two sets of coordinates. The first set, plotted along the y-axis, is the total number of target class cases, and the other set, plotted along the x-axis, is the number of observations. The line chart shows the depth of the number of cases versus the number of target class cases identified. This is called the cumulative lift curve. It shows the number of actual target class cases we are able to identify by looking at a certain number of validation cases with the highest probability of belonging to the target class predicted by the KNN model. When the lift curve arches above the diagonal line, it shows that the model is able to identify a larger percentage of target class cases by only looking at a small percentage of cases with the highest predicted probability of belonging to the target class. Now let's run this line of code. And the cumulative lift chart shows up on the right side of the screen. As you can see from our lift curve here, if we only look at the top 200 cases with the highest predicted probability predicted by the KNN model, we are able to catch about 150, which is almost all the target class cases in the validation dataset. This shows that the model is very effective in classification. We can also add a diagonal line to represent the performance of a random guess by using the lines function. Let's run it. As you can see, a red dashed line has been added to the cumulative lift chart. The diagonal line represents the performance of a random guess. So for example, if we look at 200 cases, which is about 50% of all the validation cases, theoretically, we will be able to capture about 50% of all the target class cases. In this case, about 75 cases. As you can see in the lines command, we use the color equal to red to show the diagonal line in red, and also use the line type of 2, which shows the line as dashed line. In our case, a lift curve that arches above the diagonal line indicates a better than random selection predicted performance for the KNN model. To create the decile-wise lift chart, we are going to use the bar plot function to create a bar chart. The bar plot function requires one parameter, which is the height of the bars. The height is determined by the lift of each group. It is computed as the mean response, which is the percentage of target class cases for the group divided by the overall percentage of the target class cases for the entire validation dataset. The idea is that if the cases are selected randomly, each case would have the same probability of being a target class case, which is the overall percentage of the target class case. For example, about 40% of the cases in the validation dataset are target class cases. Then it means that for any given group of cases, about 40% should be target class cases. By dividing the actual percentage of target class cases in a group by the 40% probability, you get the lift for the group, which indicates the improvement made by the KNN model. Now let's run this line of code to see the decile-wise lift chart. So as you can see from the decile-wise lift chart, the lift of the first bar is about 2.3, and it means that if we select the top 15% of the cases in the validation dataset with the highest predicted probability of belonging to the target class, we will be able to capture 2.3 times as many actual target class cases than if we randomly select 15% of the validation cases. A good predictive model should have high lifts for the first few groups, and then the lift would taper off in the later groups, as you see in this decile-wise lift chart. It means that we will be able to capture most of the target class cases simply by looking at a small percentage of the high probability cases. In the application of response modeling, which tries to identify potential customers to target for certain products or promotion, if we can capture a large percentage of the actual buyers by only targeting a small percentage of customers with the highest predicted probability, then we can save a lot of marketing dollars and at the same time run a successful campaign. Finally, let's construct an ROC curve. The receiver operating characteristic curve shows the sensitivity and specificity across all possible cutoff values. We use the ROC function, which produces an ROC object that can be used to plot the ROC curve. We then use the plot.roc function to plot the ROC curve and the AUC function to retrieve the AUC value. Now let's run these three lines one by one. As you can see, the ROC curve shows that the KNN model performs better than the baseline model, which is shown as the gray diagonal line, in terms of sensitivity and specificity across all cutoff values. And then the area under the curve, or the AUC value, is very high. It's 0.9532 indicating that the KNN model performs extremely well in predicting the gym enrollment among potential members. So as you can see here, the R code for creating the performance charts are not very complex, and in most cases, all you need to do is to modify the existing code to fit your problem. But in addition to creating the charts, it is important to understand how to interpret these performance charts. Now let's look at how we can score new cases with our KNN model. To score the records of the potential gym members, I have imported the data from the gym underscore worksheet of the gym data file into a data frame and named it my score data. The score data only contains the 3 predictor variables: age, income, and hours. As KNN uses the historical data to identify nearest neighbors for predicting future cases, the transformation of the score data into z-scores should be modeled from the historical data and applied to the score dataset. To do this, we need to use the preprocess function in the correct package. The preprocess function computes the parameters needed for standardization, which are the means and the standard deviations of the training data. We can store the parameters in an object called preprocessing. Now let's do that. Since we only need to standardize the predictor variables, so we are only going to use columns 2 to 4 in the MyData data frame. In the preprocessing function, the method option is where you specify the preprocessing you are going to perform on the data. In this case, we use a combination of 2 methods, center and scale. The center method calculates the mean for a variable and then subtracts it from each value. The scale method computes the standard deviation for a variable and divides each value by the standard deviation. So if you combine these 2 methods together, it is exactly the formula for computing the z-score. Now let's run this line. Now we are going to apply the transformation to the score dataset using the predict function and store the z-score in a new data frame called MyScoreData1. Let's try it. Now let's take a look at MyScoreData1 to make sure that all values have been converted into z-scores. It looks right. Now we are going to apply the KNN model to the standardized score dataset. We're going to use the predict function to do that. Now we're going to store the predicted class membership in an object called KNN_score. Let's run it. And now let's take a look at the predicted membership. As you can see, the results are the class memberships using the default cutoff rate of 0.5. You can always use a different cutoff value to classify, as I showed you earlier. We will put the class membership along with the original score data. And then let's take a look at the first few records. Let's first run this line. Now let's take a look at the first few records here. According to the KNN model, the first potential member, who is 22 with an income of $33,000 and works out 5 hours per week, is not likely to become a gym member. But potential member 2, who is 23, makes $65,000 and spends 9 hours exercising, is likely to become a member. As mentioned earlier, the KNN method is most often used for classification, where the target variable is categorical. However, it can also be used for predicting a target variable with a numeric value. To predict the value of a new record, the KNN method uses a similar approach with the Euclidean distance to identify the nearest neighbors, but instead uses the average of its k nearest neighbors to estimate the value of the new record's target variable. Furthermore, instead of using classification performance measures such as the confusion matrix, it will use predict performance measures such as root mean square error or mean absolute error.